Of the yes, recording in progress. Thank you very much. Welcome back, everybody, for day number 4. I'm pleased to kick us off with today's lecture on computing high energy scattering in QCD. For the last 3 lectures, we sort of started at a very high level and then zoomed in to try to get to the point of discussing what is QCD. Last time we completed the exercise of defining a gauge theory and then constructing QCD as the non-abelian gauge theory of SU3 gauge symmetry. Oh, sorry, it looks like my formula's got a little smudge from the screen. So we constructed QCD as the non-abelian gauge theory of SU3. Just thinking about that gauge group, the set of special unitary 3x3 transformations. The defining representation in terms of a 3x3 matrix is called the fundamental representation. That's the representation of the group that the quark charges live in. The generators in the fundamental representation I write as little ta, and these are just the Gelman matrices lambda a over 2. We looked at those last time, and the Gelman matrices are just generalizations of the Pauli matrices to a 3x3 configuration. That's not the only representation that's provided to us from the basic ingredients of the theory. There's also the adjoint representation. That one is built out of the structure constants FABC. And if you define a matrix that has adjoint indices BC for each of the adjoint generators TA, then you construct another equally valid representation of SU3. That satisfies exactly the same commutation relations as the fundamental one. Namely, that the commutator of the generators TA with TB gives you the structure constants I FABC times another generator TC. So these are the 2 basic building blocks of the gauge structure, the color structure of the theory, the fundamental and the adjoint representation. We talked about it for the specific case of real-life QCD, which is SU3. We compared it to the more familiar case of SU2, which normally describes spin. And then we said it doesn't really change that much if I generalize to arbitrary number of colors, SUN or SUNC. And that's particularly nice because then I can take NC to be a variable and I can take a limit of large NC where the calculation simplifies. This is known as the 't Hooft large NC limit. It has the benefits of significantly simplified color flow. One thing that comes out of that is that all large NC diagrams are planar, meaning that you shouldn't have any lines that cross underneath one another without touching. All of the propagators should be able to lie flat in a single topological plane. And the effect of going to large NC basically means that the S in SUN doesn't really matter at large N. This is one generator out of NC squared minus 1 of them. So NC squared minus 1 is practically as good as NC squared. The other interesting thing is that the large NC limit, because it picks out the dominant color space, it contains only gluons. And that may be a good approximation for the physics you care about or a poor approximation for the physics you care about, depending on whether your observable is dominated by gluons. So just keep in mind that large NC is great for simplifying the color properties, doesn't necessarily simplify anything else like spin or flavor or other quantum. So that was the color structure of QCD. Then we used that gauge group to extend the free Dirac-Lagrangian and use that gauge symmetry as the basis to define the gluon. That basically gave us this particular minimal coupled form of the interaction vertex between the fermions, the quarks, and the gluons, the vector bosons. In the process, we had to construct the kinetic term that goes along with that gluon field. And that kinetic term also contains its own gluonic self-interactions, namely a 3-gluon vertex and a 4-gluon vertex. So the really interesting parts of QCD are right here. You have the quark-gluon vertex, very analogous to what one has in QED. You have the 3-gluon vertex, which has this characteristic FABC coupling, and one of those fields comes in with a derivative so that you have a momentum dependence to the coupling. And the last one is a 4-gluon vertex. Notice that the 4-gluon vertex doesn't enter perturbation theory until next to leading order, or maybe next to leading order, however you would call it. Order G squared. All of the other terms are order G. the 4-gluon vertex is exactly as important as 2 of the 3-gluon vertices. So it should make sense that a contribution that looks like this happens at the same order as something that looks like this. It allows me to construct a 4-point function. So this is really where all of the magic is. And of this, it's really the 3 and 4-gluon interaction vertices that make QCD so unique. So the thing that I wanted to do today is to take these ingredients that we built so carefully, especially the explicit Feynman rules that go along with these vertices. I showed them last time. I don't want to try and write them on the screen again, but let me just point you to where they were in the previous lecture notes. Oh, they are here. There we go. So this figure 3.2 from last lecture has the summary of the Feynman rules. And so today I want to take those ingredients and put them to use. So now that we put all of the labor into constructing what QCD is, let's roll up the sleeves and calculate something with it. Any questions on the recap from last time? Yeah. Okay, I don't hear any questions, so let me dive on in. So what I would like to calculate today is quark-quark scattering. Quark-quark scattering in Reggie kinematics. So first I have to define my observable. The process that I care about is quark-quark scattering. So to be completely explicit, I have in mind the process of 2 quarks scattering together, and in the final state, I have 2 quarks. So this is exactly 2 to 2 elastic quark scattering. Highly analogous to electron-electron scattering in QED. If I write down the Feynman diagrams that contribute to this process, there's only 2 that I can draw. I have to have a quark coming in, and I have to have another quark coming in. They're allowed to interact with each other, and I have to have a quark coming out and another quark coming out. So about the only way that I can complete this diagram is to connect them by a gluon exchange like this. If I label my initial particle P1 and P2 and my final particles P1 prime and P2 prime, this diagram is the one that I will refer to as the T-channel diagram. I will write it as IM sub T, where M is the scattering amplitude and this is the T-channel scattering amplitude. There's a second diagram that I can draw that looks very much the same. It has the same kind of gluon exchange. It differs only in one respect, which is the exchange of identical particles. So if I have, I guess, 2 quarks of the same flavor here, here I'm implicitly assuming that I have, I don't know, 2 up quarks go to 2 up quarks. If these are identical particles in the final state, I can't tell the difference between which one is which. So I also have to add the contribution where I exchange which one I call P1 prime and which one I call P2 prime. So that diagram looks the same on the left-hand side, but then I scramble which one is P1 prime and which one is P2. These are the 2 diagrams. This one I will refer to as the U-channel diagram. IMU. In principle, it's there. It also makes a contribution to this amplitude. I said that the U-channel amplitude is related to the T-channel amplitude by the exchange of identical fermions. What should I do if I exchange 2 identical fermions in the amplitude? What should I not forget about fermions when I exchange them? They follow Fermi-Dirac statistics. What does that mean if I take 2 identical fermions and I exchange them?
You pick up a minus from the anti-symmetry.
Exactly. They're anti-symmetric under exchange of identical particles, so that I don't add the two amplitudes together, I subtract them. Or equivalently, I could say this minus sign is included in the Feynman rules for this. So overall, this is my content of the scattering amplitude IM for lowest order port scattering, elastic scattering of this. So that's the problem I'd like to pose. I'm interested in computing these two Feynman diagrams. You could calculate it for arbitrary kinematics. It's not that hard. But I'm particularly interested in one limit of the kinematics, which is the high energy limit of the kinematics. So if you calculated 2-to-2 scattering amplitudes, you surely encountered the Mandelstam variables, which are the most natural compact way of describing the kinematics. For a 2-to-2 process, I can define three Mandelstam invariants, S, T, and U. S is the invariant center of mass energy, P1 plus P2 squared, and by momentum conservation, that's the same thing as P1 prime plus P2 prime squared. T is the invariant momentum transfer. That's the difference between particle P1 coming in and P1 prime going out. And by momentum conservation, that's the same thing as P2 prime minus P2. And then U is the only remaining independent combination. That's a scrambled up combination that mixes initial state and final state, and it mixes particle 1 and particle 2. So this is something like P1 minus P2 prime squared, which is the same thing as P1 prime minus P2 squared. The Mandelstam invariants are the most natural way to describe the kinematics of this process. I am interested in these Feynman diagrams, not just in arbitrary kinematics. I want to know what happens when I take the limit where the energy goes to infinity. The trick is there's not one unique way to take the limit as the energy goes to infinity. There are really more like two. To see why there are two limits, I can describe everything in terms of the Mandelstam variables, but I need one other piece of information. Not all three of them are independent. They satisfy a constraint equation that comes from the on-shell conditions. So if I have four identical particles, then the sum of S plus T plus U is 4 times the mass, the invariant mass m squared of the particles. In general, it's on the right-hand side, it's the sum of the masses squared of all of the particles. For this simple problem where I've got 2 identical particles in and 2 identical particles out, I get 4m squared. So for my purposes, I'm going to think of S and T as independent variables, and U is constrained to be 4m squared minus T minus U. So really, I've got 2 variables, S and T, and that's the rub. I can take S goes to infinity, but I need to specify what happens to T, or equivalently, what happens to U. So there are 2 highly distinct limits in which I can take the energy S to infinity.
Matt, can I ask a question quickly?
Yes, please.
Yeah, sorry, my internet dropped for a second, so you might have said this, but why are we ignoring the S-channel diagram in this case?
There is no S-channel diagram for this particular amplitude because I've chosen to have a quark and a quark, so there is no fusion channel for them to combine and then split. If I had done quark anti-quark, then there would be an S-channel diagram.
Oh, okay, that makes perfect sense. Thanks.
It's just this particular observation. In a moment, I'm going to throw out the U-channel diagram as well. So there are 2 very different high energy limits. So I can take S goes to infinity, and one possibility is that I also take T goes to infinity. T typically is a negative number, so it makes more sense if I say absolute value of T goes to infinity. This is a limit where I put in infinite amount of energy into my LHC collider. I have a huge amount of square root S going into the beam pipe. But I also have a huge amount of momentum transfer. There's a large amount of PT as well. So this is the limit where my particle comes in with energy comparable to square root of S. it scatters and then it goes off. It still has longitudinal momentum comparable to square root s, but now it picks up a PT comparable to, let's say, square root of Mandelstam t. This limit is the one where both the energy and Mandelstam t are getting large at the same time. So if both sides of this triangle are getting large, this is the limit where I can scatter out a large n, because I have a large PT coming in from the transverse momentum exchange, the Mandelstam t. This limit is known as the Bjorken limit. Bjorken kinematics.
I just have a question.
And this, by the constraint condition, this means that U, which is 4m squared minus t minus s, this thing is going to minus infinity.
Matt, there's a question.
Question, yes, please.
Yes, I just want to ask, I don't know if I fully understand how T is related to PT, how increasing that will, how it's related.
So let me come back to that in a moment. I think that'll be very clear in a second when we work out the kinematics in light front coordinates for this process, and then we calculate explicitly what is T in terms of PT. It will turn out for the process that we're calculating now that the Mandelstam T is basically going to be minus the transverse momentum exchange squared. So we'll show that in a moment.
Okay, thank you.
Sure, no problem. Okay, so this is one type of high energy limit. This is the high energy limit where the scattering angle can remain large. So this is a hard scattering limit. It allows for potentially large angle scattering. And in the language of deep inelastic scattering, this is the so-called large X limit. This is typically the kinematic limit that one is working in if you want to extract Parton distribution functions from something like deep inelastic scattering. You take the limit where the momentum transfer T, in that process you typically call it Q squared, to infinity, a very hard PT momentum exchange. And you also have a very large center of mass energy. The relationship between those two quantities in DIS is coming from Bjorken X. So for those who are familiar with the terminology, this Bjorken kinematics is the large X regime. That's not the limit that I'm interested in here. The limit that I'm interested in here is the one that I alluded to previously. That is the forward scattering limit. That's what I get if I take S goes to infinity, but T is held constant. This is known as Regge kinematics. I can take center of mass energy to infinity, but now Mandelstam T is held constant. This means that now when I have my scattering process, I have a very large square root S going forward longitudinally down the beam pipe. My transverse momentum PT, which is like square root of Mandelstam T, is constant. So now this transverse leg is constant. The long leg is getting very, very long. And so my scattering angle theta tends to 0. This is the forward scattering regime. That scattering angle, loosely speaking, is ET over root S, and this is going to 0. In the language of deep inelastic scattering, this is the small x limit. So this is the limit that I want to examine the quark-quark scattering processing. The high energy limit tends to simplify the kinematics quite significantly. But you get very different physics depending on which high energy limit you take. Okay, so first things first, let's work out the kinematics of the process. For a high energy scattering process, the easiest way to describe the kinematics is in terms of light front coordinates. Also called light cone coordinates. These are defined as a linear combination of the time light and longitudinal space-like components. It's basically a rotation of your coordinate system. If I have the z component of momentum along the horizontal axis, the time-like or energy component along the vertical axis, then this linear combination describes the line y equals x, that's the light cone plus direction, and the line y equals minus x, that's the light front minus direction. And those are very natural coordinates to use when describing the behavior of particles scattering in light-like kinematics, s going to infinity. One thing that's particularly nice about the light front coordinates is if I know one of my variables is going to be large, like if I know that my particle, let's say P2, is coming in with a very large amount of energy going down the light front plus direction. If my momentum P2 mu is made up of components P2 plus, P2 minus, P2 perp, these components are not all independent. They have to satisfy an on-shell condition, P2 squared equals m squared, in general. When I take these light front coordinates and I use this definition, P2 squared is a set of cross terms, 2P2 plus, P2 minus, minus the transverse component P2 perp squared. And if this is equal to a constant m squared, I can solve this relation for one of the light front. So for instance, I can solve it for the small component P2 minus, and I get P2 perp squared plus m squared over 2P2 plus. So this is what the representation of an on-shell condition looks like in light front coordinates. It's very convenient because I can pick this variable is my interesting one, that's the large momentum component. This variable is then small. Notice that it's transverse stuff divided by my huge momentum P plus. So typically this number is going to be small, approximately 0 in the minus direction, if your particle has a huge amount of momentum going along the plus direction, and vice versa. So for an ultra-relativistic particle, you have a large component in a particular light front direction, and that typically gives you a very small component in the opposite light front direction. That's really the beauty of it, is that allows you to disentangle the kinematics of things that are going in the plus direction at the speed of light from things going in the minus directions. So in terms of these variables, I want to write down the kinematics of my scattering process. I strongly recommend when you're performing any calculation for the first time, the first thing that you should get a concrete handle on is the kinematics of the scatter. So let me just draw one of these diagrams. I'll draw the T-channel diagram. So first thing that I can do is choose a coordinate system. I'm going to choose my incoming 2 momenta. That's equivalent to specifying my initial frame. So I will choose to work with P1 momentum, which is going along the light cone minus axis. So I'll pick P1 minus. I'm going to choose it to have 0 transverse momentum. And if I have something going along the minus direction with no transverse momentum, the only source of plus momentum is its mass. Right? This term is 0, and I get mass over P plus. For simplicity, I'm going to also work in the massless limit, just to make the algebra of today simple. So if I work in the massless limit, then my plus momentum is exactly 0. I have no mass contribution, and I'm working in a frame where I have exactly 0 transverse momentum. So my initial condition is that P1 is moving exactly along the light front minus axis, just like this. Similarly, P2, I choose to be moving along the light front plus axis. And for the same reasons, P2 has a large plus component, exactly 0 minus, and exactly 0 transverse. This is what I choose by setting up the problem. What I don't choose is what happens thereafter. So let's see. Yes. So now then I calculate the scatter momentum. So my P1 prime Yes. So for my P1 prime, I want this one to scatter out, carrying some fraction of that light front minus momentum. So I have P1 prime minus, and I have some transverse momentum, P1 prime perp, P1 prime plus in general. What I'm trying to say here is that the kinematics that's going to dominate the scattering, which we'll show in a second, is the one where all of that plus momentum, I guess here it's minus momentum. I've got a large light front minus momentum of order square root of s that comes in here. The dominant configuration is that that momentum goes straight out into the finite state. If I start to send large amounts of momentum through the propagators, I end up with a large suppression factor for the diagram. That's exactly what happens for the U-channel, by the way. The U-channel diagram looks like this. In the U-channel diagram, I have a large amount of minus momentum coming in here in the form of P1 minus. But particle P1 prime comes out going in the forward direction. So if I have a large amount of minus momentum, I have to send it through the diagram and back out. Likewise, if I have the large plus momentum coming from P2, I have to send that through the U channel and back out. So I end up sending large amounts of virtuality through my propagator. This U channel diagram has a propagator that is 1 over U. And as we saw in this limit, magnitude of U is blowing up to infinity. That's exactly what this kinematics is. So in the Reggie kinematics and forward scattering limit, the back scattering channel, which is the U channel diagram, is suppressed. So I forget about the U channel. And then in that case, I only have T channel. The dominant scattering is the guy who came in along the plus Z axis keeps going along the plus Z axis. The guy who came in along the minus Z axis keeps going along the minus Z axis. So what that gives me is P1 prime. The amount of minus momentum coming out here is approximately the same as the amount coming in. The amount of, all right, I'm arguing this backwards. Let me finish writing what I'm saying and then I'll justify it better than what I've said. So, P2 prime, then the scattered one. This one has the large minus momentum, and therefore, since it's on shell, its plus momentum is very small. So this is, again, approximately 0 in the minus direction. Strictly speaking, it's not 0 from the on-shell condition. It's P1 prime perp squared over 2 P1 minus. But since P1 minus is very large, this component is very small. For the same reasons, P2 prime comes out primarily with that P2 plus momentum that came in down here. It goes out with 1 perp prime squared over 2 P2 plus. And then it has the recoil momentum negative P1. Okay, so let me try and draw that scattering kinematics again. When I work with the light front coordinates, basically I can trace separately the flow of light front plus and minus momentum through the diagram. So in this setup, I have P1 minus that comes in from the upper line. And that P1 minus comes in and it goes right back. The same huge amount of momentum, P1 minus going to infinity, flows straight in and straight out. It never passes through a propagator. In the same way, the large P2 plus flows in from the bottom and out from the bottom. That large momentum, which is also of order root s going to infinity, also never flows through the propagator in between. And then there's a transverse momentum, which you may have that is much smaller than this, something of order T instead of order S. That momentum transfer is your P1 perp, and this is much, much less than square root S. So that's the transverse recoil, P1 perp this way, negative P1 perp that way. Okay, I fumbled and waved my hands a little bit here for the kinematics. A better way of saying what I was trying to say is to write it down and enforce the momentum conservation. So I had P1, P1 prime, P2, and this P2 prime is P1 plus P2 minus P1. Maybe an easier way to constrain this is to call this Q, which is P1 minus P1 prime, in which case this is P2 plus Q. So how do I find the constraints that I just kind of waved my hands at here? I use the on-shell conditions for my particles. I know that my P2 minus was 0. This outgoing particle, P2 prime, has its components determined from the on-shell conditions and momentum conservation. So if I want to know what is Q minus is related to this component, P2 plus Q minus, and P2 minus. So I think of the minus components here as being set by the on-shell conditions from the pluses. The pluses are the large component down here. And by momentum conservation, if I want to know what Q is, then I get it from these two external orders, the difference between one and the other. The P2 minus is 0. This thing follows from the on-shell conditions, which we said is P1 perp squared over 2. And in general, it's P2 plus Q plus. And as we'll show in a second, Q plus is small, so I throw it away. This is approximately P1 perp squared over 2 P2 plus. And this is very small. This is approximately 0. So that's a better way of saying what I was trying to say before, that the amount of plus momentum that came in here all goes out there. Better way to say it is, let me calculate how much plus momentum went through the middle, and I found almost 0. In the same way, I fixed the plus momentum component from the upper half of the diagram. So I had a large minus momentum flowing up here. And then my minus momentum is set by the on-shell conditions. Right, I'm fumbling something about the statement here, but this demonstrates from the on-shell conditions down here that your Q minus is 0. Similarly, the on-shell conditions up here demonstrate that the plus component is 0. The combination of on-shell conditions here and here tell you that Q plus is of order some transverse momentum scale over P1 minus that also goes to 0. So that's the argument for sort of where the kinematics comes from. The important punchline is this one. That effectively your scattering looks like P1 mu is nothing in the plus direction, large momentum in the minus direction, nothing transverse. P2 mu is something large in the plus direction, nothing in the minus, nothing in the transverse direction. P1 prime mu is 0 plus, P1 minus, P1 prime perp. P2 prime mu is 2 plus, 0 minus, negative P1 prime. So this is the kinematics that we want to use to evaluate the amplitude. The amplitude we get from the Feynman rules. So I had P1, P1 prime, P2, P2 prime. So let's see, if I follow the Feynman rules, the way that I normally implement it is that I start at the end of the fermion line and I work backwards, reading the Feynman rules as I go. So the Feynman rules tell me the scattering amplitude IM. I'm looking at just this particular diagram, which dominates the Reggie kinematics, the forward scattering kinematics. So if I start with that final state particle, it's a spinner, it's an outgoing quark. That's represented by the spinner U bar. Instead of writing down all of its quantum numbers, I'm going to write the shorthand U bar 1 prime to know what particle I'm talking about. Then I have the vertex afterwards. This is the QCD vertex, which is IG gamma mu TA. So I've put mu and A as my indices on this particular vertex. And then I had my incoming fermion, which is the U spinner of particle number 1. Similarly, on the lower line here, I have an outgoing spinner U bar of particle 2 prime. I have the counterpart vertex here, IG gamma nu TB 2. So here I call this nu and B. I've got the 2 vertices, and then the last thing that I need is the propagator for the gluon. That is minus I G mu nu in Feynman gauge. The propagator changes depending on what gauge you're in. For simplicity of the calculation, I'm going to work here in Feynman gauge. In Feynman gauge, the numerator is simply this G mu nu instead of having a bunch of extra terms in it. And I divide by the virtuality, which in this case is Q squared, which is E1 minus E1 prime squared, plus I epsilon, but I don't need the I epsilon here to regulate the singularity. And then I have, sorry, I guess the G mu nu should be upstairs to match here, and then a Kronecker delta AB for colors. So I can clean everything up. This denominator, by the way, is precisely Mandelstam T. This T channel diagram exactly has T, which is flowing through that propagator. So when I put everything together, my scattering amplitude is, if I move the I to the other side, IG squared divided by T. I have 2 color matrices, TA and another TA. Maybe I should be careful here about what colors go in. If I specify the initial state color as I and the final state color of particle number 1, I prime, and similarly the colors here are J and J prime, then this TA has color indices I prime I, rotates to color I prime from color I. This one is J prime J for the same reason. So this is I prime I, J prime J. Yes. I think I've taken a different notation than what's in my notes. Sorry about that. And then the simplified spinner part is U bar 1 prime, gamma mu U2. No, that's the U channel. 1, U bar 2 prime, gamma upper mu U2. We could write down the same kind of expression for the U channel diagram. As I said before, it's going to have a 1 over U in it. And in this limit, U going to infinity kills off the U channel diagram. Okay, so this is our basic building block for the amplitude. Maybe I should pause here. Any questions so far before we square it? Not yet, okay. So when I square the amplitude, I'm going to calculate the cross-section. The cross-section comes from the amplitude squared, which is the sum then averaged over all quantifiers. So that means for us, I have to sum over all final state spins. I have to average over all initial state spins. I have to sum over final state colors. And I have to average over initial state colors. And then I have the amplitude squared for each individual combination of spins and colors. So the spins part of the equation works exactly the same way that it does in QED. There I sum over spins and I use the identity sum over spins U PS, U bar PS is P slash plus M. And if I'm working in the massless limit, I don't even care about the M. But I can turn repeated U and U bar after summing over spins, I turn them into slashed momenta. And when I do that systematically for everything in my amplitude square, I turn everything into traces. So the usual trick is use this identity or versions of it many times and turn everything into traces of gamma names. That's still how we're going to handle it here. But now there's a really interesting new ingredient, which is the color algebra. There are also new color traces to compute that lead to a color factor coming from the non-abelian QCD degrees of freedom in the possible. So I need to square this thing, and then I need to set up those summations. I think it's very helpful before I actually write the calculation to sketch it as a cut diagram. So the cut diagram, or the amplitude squared, can be compactly written with this cut diagram notation that looks like this. If you're not familiar with this, the way that it works is that the left-hand side represents the scattering amplitude IM. So this is exactly the diagram I had a moment ago. P1 comes in, P1 prime goes out, P2 comes in, P2 prime goes out. In this process, time is effectively flowing from left to right. T equals minus infinity is the initial state over here. And this vertical line, which is referred to as a cut, denotes T equals plus infinity, the final state. The reason for writing it in this funny form is because now I can write down not only the amplitude, but also its partner, the complex conjugate amplitude that goes with it. This, in this combined picture, looks like it's going backwards. Here, time runs from T equals minus infinity over here, and T equals plus infinity is again the cut in the middle. So it's like amplitude on the left, conjugate amplitude on the right. Time starts at the initial state on the ends, and it flows in and falls down this sink in the middle. That's the final state. This is a very nice way of representing the single combined diagram that will give us the answer after we square this. So when I do the spin sums, for instance, I'm basically going to be tracing, starting along one of these lines back in time. When I get back to the initial state, this initial state is the same as this initial state. So it's almost like that line continues back around. And I have a single trace over that upper part of the diagram. Separate trace over the lower part of the diagram. That's what's going to give me the structure of the answer. Okay, so now that you have a picture to anchor your calculation to, what do I get? If I square this thing, then the summation that I have to do is 1/4 from the spin averaging. Because I have two choices for the initial spin of this quark, two choices for the initial spin of that quark. So the averaging of the initial spins is 1/4. I also have many colors. It's easiest to do the color algebra in the general SUNC color group. So I'm just going to keep NC arbitrary. It doesn't really change much of anything about the color calculation. Here, if that's the case, I have NC number of colors to choose from for this quark, also NC colors to choose from for that quark. So the number of possible colors that I average over is 1/NC squared. And then I sum over all of the colors in the problem. And then this is my individual T-channel amplitude squared, which is shown above. So now if I open up that the absolute value squared, I have a prefactor of 1/4NC squared. I'm summing over all spins. I'm summing over all colors. My prefactor from everything gives me G to the 4th over T squared. I have now two products of these color matrices. I have the original TA, I prime I, the TA, J prime J. But now I also have another pair with the same structure. It's complex conjugated. So I get, if you like, CB, I prime I, CB, J prime J conjugate. But since the T's are permission, when I complex conjugate the thing, that's equivalent to reversing the indices. I prime, and J prime. So that's my color matrices. I also have the spinor products. From the amplitude, I had U bar 1 prime gamma mu U1. and the partner U bar 2 prime gamma upper mu U2. When I complex conjugate this thing, I get another set of spinor products that get read backwards. The complex conjugate of the spinor product is basically the thing read backwards where you swap the bar and unbarred spinors. So the conjugate of this first expression is U1 bar. I have another gamma matrix, gamma nu, U1 prime. And then I read the other one backwards as well. That one looks like U2 bar, gamma upper nu, U2 prime. Okay, I think I've got everything. I've got the averaging prefactor. I've got the coupling and the virtuality. I've got the color factor. Notice that the color factor structures itself into 2 separate traces. I have a TA I prime I and a TB I prime. That describes exactly this TA at this vertex, TB at that vertex. And the color flow, just like the particle number flow, is connected into a single trace. So I get a trace from this upper line of the color matrices TA and TB. Incidentally, I also get another trace of exactly the same form from the lower line. So that's what's about to happen to the color structure. That's about to collapse into traces. The same is about to happen to the Dirac spin structure. When I sum over the spins of any repeated spinor particle down here, I turn that UU bar into a P slash. So for instance, this factor and this factor, when I sum over the spins of that U and that U bar of the same particle number 1, that gets turned into P1 slash. Similarly, that U1 bar prime and that U1 prime get turned into a P1 prime slash. And the 2 things together combine into an overall trace. This overall trace of P1 and P1 prime now over their direct structure. Okay, so that was a lot of words and a lot of algebra by pointing. Let's write down the structure of the answer now. So I get average T-channel amplitude squared is 1 over 4 NC squared. I have G to the 4th over Mandelstam T squared. Then I have trace of TA-TB, another trace of TA-TB. And then I have the fermion traces, trace of E1 prime slash gamma mu, E1 slash gamma nu, trace of E2 prime slash gamma mu, E2 slash gamma mu.
Hi, sorry, Matt.
Yes, please.
Well, before you get rid of that.
Oh, yes, thank you.
So just talking about when you do the spin sums over the spinners at the bottom.
Yes.
So when we do that spin sum, are we effectively summing over 1 prime and 1 indices independently? Is that why we can sort of separate out that multiplication?
Yes, so let me try to show all of the indices on that particular product to make sure it's all explicit. I'm going to eliminate everything except just the minimal example here from that spinor product.
Okay.
So to write it out more completely, I start out with, I want to sum over, let's say, spin S1 and spin S1 prime. And I've got 2 factors. The first is U bar of E1 prime S1 prime. Then I have gamma mu, U of E1 S1. And then I have another U bar E1 S1, gamma mu, U E1 prime S1 prime. So there are 2 independent sums that are going on, S and S1 prime. And so those 2 sums will couple to these things differently. The next step is I write down this thing explicitly in terms of Dirac indices. So if this has indices, let me call it capital I, capital J, then this has index capital I, this has index capital J. In the same way, this would be K, this one is KL, and this one is L. Those are the indices 1, 2, 3, 4 of the component of the Dirac spinor matrix. Now, once I've written the indices completely explicitly, now I can perform this summation. So this part I can do sum over S1, U P1 S1 with index J, U bar P1 S1 with index K. The result from doing that is P/1 plus M indices J, K. So I think a part of the question is about how do I know what indices connect to what? Why am I allowed to pick out this U bar 1 prime U1 and then slide it past the other factors?
Yeah.
The reason is because of how the indices are connected with each other. If you write down this sort of I, J, J, then there's no ambiguity. This thing is overall scalar. So I can take that object and move it around past anything else which is a scalar. And as long as I remember which indices are contracted with it, in which other indices, I can take individual factors and move them around too, as long as I keep the structure of the summation. So that's what we're doing here, is I'm taking this JK element and turning it into P/JK element. In this massless limit, I don't even have this piece. The other one is I have sum over S1 prime of, if I write it in the other order, U P1 prime S1 prime with index L, U bar P1 prime S1 prime with index I. After I sum over S1 prime, I get P1 prime slash with indices Li. So the indices will keep track of it for you and tell you how to connect the pieces into an overall matrix product. And the result when I do this is, so I started off with sum over spins. I had U bar 1 prime gamma mu U1, U bar 1 gamma nu U1 prime. So the result of doing this was I turned this into a P1 slash that now by order of the matrix multiplication is sitting in between the gamma nu and the gamma mu. That's what that IJKL index structure tells me.
Yeah.
The other one, which is maybe not so obvious, is that this one becomes a P slash that wraps around the end. This one was something that had the very first index I and the very last index L on it. So it sort of wraps around the P1 prime slash into a trace. It connects the very first and the very last. So that is in detail how it works. The indices tell you how to connect the product, and that when all of the sums are completed, there's no free indices left. So they have to assemble into a trace. That's the only thing.
Okay. Yeah, and just to check, because the first term, the first term on the left in the full sum, because that whole thing is a Dirac scalar, we don't need to worry about moving it past things in terms of commutations.
Yeah, exactly. Yeah, this thing overall has no free indices. This is a Dirac scalar.
Okay.
So these are just numbers. They're not quantum operators. There's no operator commutation to worry about. So if I specify the index ij, this is just a number, a C number that we use.
Okay, that makes sense. Thank you.
Okay, cool. So that was how we get the Dirac trace structure and the color trace structure. Okay, so let's play with the color structure first. This is the fun new ingredient. Here it's just an exercise in the color algebra of SUN. In general, the generators TA and TB are trace orthogonal, just like the Pauli matrices are. So if I have any two of them, the trace gives me something proportional to the Kronecker delta AB. The generators of SU2, the Pauli matrices, satisfy the exact same identity. Another identity which is helpful is the sum of the squares of the generators. So if I have two matrices TA times TA, and I sum it over all 8 of the generators A, the answer is a number called CF times the identity matrix. This object is called the quadratic Casimir. It's a special, like, topological invariant of the group, sort of like the norm or the magnitude of the generators. This is just a number. In QCD or in SUN, that number is NC squared minus 1 over 2NC. This number is CF, and if you're working in NC equals 3, which is strict QCD, then CF is 8 over 6, which is 4/3. And then the last thing that we'll need is trace of the identity matrix. Keep in mind here that I'm talking about fundamental representation. So this is the 3x3 matrix or the n by n matrix in SUN. So trace of identity, that's really the NC by NC identity matrix. So that trace gives me NC. If I have all of these things together, now I can evaluate that double trace directly. I think I'm going to combine that together with, no, I'll save that for the other factors at the end. So if I just start with trace TATB, trace TATB. For the first trace, I'm going to use my trace orthogonal identity as 1/2 delta AB, trace TATB. Then I use the Kronecker delta inside the other trace to get 1/2 trace of TA times TA, but TA times TA is the quadratic Casimir. So that's 1/2 times CF times trace of the identity matrix, and trace of the identity matrix is NC. So this expression is NC CF over 2. That is my color factor for this diagram. That's strictly speaking just the color factor that came from the numerator algebra. There's still the 1 over 4NC squared sitting up front from the average. So that was the color traces. We have something very similar for the Dirac traces. One of the identities for the Dirac traces is if I have 4 gamma matrices, then everything gets expanded in all possible pairs using the metric test. So I get P1 prime mu, P1 nu, plus the other way around, P1 prime mu, P1 mu, minus the cross term, which is P1 dot P1 prime d mu nu. So I can do this for one trace, I can do it for the other trace, P2 prime slash gamma mu, P2 slash gamma nu. This is P2 prime upper mu, P2 upper mu, plus P2 prime upper mu, P2 upper mu, minus P2 dot P2 prime G upper mu nu. And this gives me the first trace, this gives me the second trace, and then I just need to multiply them all together. When I multiply those two traces out, I get 2 times P1 dot P2, P1 prime dot P2 prime, plus 2 P1 dot P2 prime, P2 dot P1 prime, minus 4 P1 dot P1 prime, 2 dot P2. That's just the dot products that I get by expanding out all of the traces. And then the last step is to combine everything into a sensible form by replacing these dot products in terms of the Mandelstam invariance. The general form of the Mandelstam invariance can be a bit messy, but it's really nice in the massless limit. For instance, I had S was P1 plus P2 squared. If I open up those parentheses, that's P1 squared plus 2P1 dot P2 plus P2 squared. But if I'm working in the massless limit, P1 squared is 0. So is P2. So S is just equal to that cross product 2P1 dot P2. And since I could write the same thing as P1 prime plus P2 prime squared, it's also the same thing as 2P1 prime dot P2 prime. So it's really easy. I just look at the Mandelstam invariant, P1 plus P2 squared, or P1 prime plus P2 prime squared, and I pick out the cross term. And it works the same for T and U. So if I want to identify what nanostem invariance each of these things is, I just need to look at which momentum goes into it and figure out whether ST or U is the one that connects those to each other. So this first factor, P1 dot P2, that's S. So this is a factor S over 2. This is P1 prime and P2 prime, that's also S over 2. These ones are mixed. This is P1 and P2 prime. That mixes primed and unprimed, and it mixes 1 and 2. So this is going to give me nanostem U with a minus sign, because U and T are differences of momentum, not sums. This one is also a mixed product, which is another minus U over 2. And then the last one here, P1 dot P prime is minus T over 2. So is P2 dot P2, also minus T. So finally, I think we've got all of the ingredients. The average amplitude squared, I've got a prefactor 1 over 4 NC squared. I have G to the 4th over T squared. Now I've done the rest of the numerator algebra. The color factor gave me NC CF over 2. And the traces, wait, I don't know if I correctly kept factors of 4 when I was writing that out here. But after all of the factors of 4, when you do those traces, the rest of the algebra gives me, I guess it's a factor of 16, because I had 4 from this trace and another 4 from that trace. So that gives me 2 S over 2 squared plus 2 minus U over 2 squared plus, minus 4 minus T over 2 squared. As I said before, you could calculate this thing for arbitrary S, T, and U, but for our purposes, I only care about it in the Reggie limit. So I want S going to infinity. That makes this term important. But T is fixed. T is constant. So in Reggie kinematics, this term is negligible compared to this term. U is also blowing up. Remember, U is going to negative infinity. So in this limit, Reggie kinematics, my U is equal to negative T minus S, and the T part is even negligible. So U is equal to negative S in these kinematics. Now I put everything together. I've got the 16 and the 4, so that's 4 times, I've got 4 from this and another 1/2 there, so that's 2 CF over NC, G to the 4th over T squared, and then I'm left with S squared over 2 plus another S squared over 2. So I get 2 CF over NC, G to the 4th, S squared over T squared. Slide. Make sure I got that right. Yes. Yes, 2G to the 4th, CF for NC, yes, perfect. All right, so that's my amplitude squared. The last thing is just to plug it into the formula for the cross section. The formula for the cross section has this bizarre expression. The sigma is 1 over 2 E1 to E2, absolute value of the relative velocity, V1 minus V2, base factors for particle 1 prime and particle 2 prime. Then I have my average amplitude squared times a momentum conserving delta. 2 pi to the 4th. Delta 4 of P1 plus P2 minus P1 prime minus P2 prime. This formula comes about, by the way, from a calculation of the probability density for a scattering involving an overlap of 2 beams with different profiles as a function of impact parameter. So if you want to know what the infinitesimal probability of scattering is, That's a product of the density per unit area of beam 1 times density of unit area per unit area of beam 2 times the cross section, which has units of area, integrated over impact parameter, which has units of area. That overall product is the expression for the probability current, the overall probability of scattering. So that's what gives you this formula when you derive it. For our purposes, the prefactor is pretty simple. 1 over 2e1, 2e2 relative velocity. The relative velocity in this frame is 2. Everything is coming at each other at the speed of light. So this is 1 over 8 e1, e2. I can easily convert those into the light front coordinates. My large e2 plus was e2 plus e2z over square root 2, where in regikinematics, p2z is about the same as the energy. So this is approximately square root 2 p2. Same reason p1 minus is approximately square root 2 e1. So I can write this expression as 1 over 4 e1 minus e2 plus, and this is exactly 1 over 2s. The center of mass energy squared. So the flux factor here is just 1 over 2s. There's a non-trivial change of variables that I think I'm going to ask you to play with on your own for homework. So whenever you have a few minutes, convince yourself that dpz over energy is the same thing as dp plus over p plus, which is the same thing as dp minus over p minus, which is the same thing as a differential unit of rapidity, where y is 1/2 log of p plus over p minus. All of these are completely equivalent ways of expressing the same phase space. So instead of calling it d3p over 2e, I'm going to call that d3p over e is the same thing as d2p perp. And then I can choose, depending on whether I want to talk about plus or minus, dp plus over p plus or dp minus over p minus. So apologies for doing proof by erasure, but to manipulate the formula on the top, the flux factor is simplified to 1 over 2s. The particle 1 phase space has a large minus, so I write that as 1 over 2 pi cubed 2p1 minus d2p1 prime perp dp1 prime minus. Then I do the same thing for particle 2, but with the large plus. d2p2 perp prime dp2 prime plus 2 pi cubed 2 p2 prime plus. I know what my amplitude squared is. And then for the momentum conserving delta function, I have conservation of all of the light front components. So I have times 2 pi to the 4th delta of p1 prime minus p1 minus delta of p2 prime plus minus p2 plus, and then delta 2 of p1 prime per plus p2 prime. Okay, so here I've used the high energy kinematics. I'm assuming that particle 1 prime goes out mostly in the same direction as particle 1. Particle 2 prime mostly goes out in the same direction as particle 2. That allows me to integrate over 3 of these variables. So I can integrate over p2 prime plus and fix it by using that value of the delta function. I can integrate over p2 prime perp and fix it using that delta function. I can also integrate over p1 prime minus and fix that integral from the delta function. But I'm left with a transverse momentum element left. So I get d sigma equals 1 over 2s. My overall factors of pi are 2 pi to the 4 upstairs, 2 pi to the 6 downstairs. So I've got 1 over 2 pi squared. The phase space element that's left is d2 p1 prime perp. I have various flux factors downstairs here. So I had 2 and 4, P1 minus P2 plus. And then I have my amplitude squared. I'm almost there. This last factor is another factor of 2s. So I can write the cross section d sigma d2 p1 prime per equals 1 over 2 pi squared scattering amplitude divided by 2s squared. Where it just so happens that the combination of the flux factor 1 over 2s and the final state phase space, another 1 over 2s combine to make it look like I just rescaled the scattering amplitude by 2s. So we already calculated this. I just divide out the 2s from in front of it and divide out 2 pi squared. And I immediately get my cross section. So the observable cross section is 4 alpha s squared CF over 2nc 1 over P1 per prime to the 4th, where I've written the strong coupling is G squared over 4. Okay, so that is the final result of the cross section. We find something that has a simple color factor. It has the characteristic perturbative power spectrum, 1 over PT to the 4th. That's the typical Coulomb scattering. We had 1 over PT squared in the amplitude, square it again, and you get 1 over PT to the 4th. The really important thing for us here is that in the limit s going to infinity, this cross-section is unsuppressed. So if I take this cross-section, take s goes to infinity, no suppression. It's still large even at high energy scattering. That is a specific consequence of the fact that we had a vector boson being exchanged. We had P1, P1 prime, P2, P2 prime, and the thing that was communicating between them was the gluon, the spin 1 vector boson. And the fact that it's a spin 1 vector has everything to do with the fact that this cross-section is unsuppressed or scaling as s goes to infinity. That is only true if you exchange a spin 1 vector boson. So spin 1 vector bosons being exchanged in the T channel leads to unsuppressed high energy scattering. You can show that on general grounds, if I exchange a particle with a different spin, something with less spin than spin 1, I actually get suppression of the cross-section. So if I have an amplitude where a quark is being exchanged instead of a gluon, then instead of getting something that goes like s to the 0, I get something which is suppressed like 1 over s. So I lose a power of the energy for every increase, or I guess decrease in the spin here. If I go from a vector down to a spinner, I get 1 power of energy suppression. If I take it down to a scalar, if I had scalar exchange in the high energy limit, then I would be doubly suppressed. I would be down by 2 powers of the energy. So there's something very special about T-channel vector boson exchange at high energies. It leads to unsuppressed cross-sections, which means if I want to do lots of these scatterings, I can. The only price that I pay is more alpha s's. And if alpha s is not that small to begin with, that's not a very big suppression. So in very high energies, multiple scattering of this type is highly enhanced. That leads to this sort of Wilson line dynamics that I know Thomas has talked about already. Okay. I'm sorry again that I fumbled the kinematics in the first place. I think what I should have done is describe it like this, where I have P1, P2, and then call this P1 plus Q and this one P1 minus Q. That would have been a much better way to get Q minus from, Q plus from P1 plus Q plus minus P plus and Q minus from P2 minus P2 minus Q. And that will immediately tell you that your Q plus is approximately 0, your Q minus is approximately 0 from those on-shell conditions.
Hi.
Yes, please.
So there's 2 forms of suppression that happen here, right? One that kills off the U channel and one that is sort of suppresses any non-vector boson scattering. Are those related in any way, or are they just entirely independent?
No, I think it's the same suppression. The U channel suppression, my IMU, goes like 1 over S in these variables. If I pick S and T as the independent variables. So the cross section that comes out of this, I should say the amplitude squared would go like 1 over S squared. So
right.
This is power suppression in S. It's exactly the same power suppression in S that I'm talking about here. So I would say, if I'm working to leading power in the energy S, I can forget about U channel, I can forget about anything but vectors. This is called the Eichenal limit, or the Eichenal approximation. If I want to go beyond the Eichenal approximation to include a power suppressed correction, probably there are some kinematic corrections, things that I threw away that would have been 1 over S. And then there's also things like exchange of quarks that would also come in with 1 over S. I think the U channel is not going to show up for at least a couple of orders in subeichenal polyactin. But eventually, if you include enough powers of 1 over S, this correction will show back up. The other particles being exchanged will also show back.
Okay. Thank you.
Sure. I should mention, just so that you've seen the terminology if it hasn't been discussed so far, the kinematics of these gluons that come out, where they have essentially no plus momentum, no minus momentum, but finite Hertz momentum, such that their virtuality is approximately 0 plus, 0 minus, minus 2 Hertz squared, so it comes completely from their transverse momentum. These are referred to as Glauber gluons. Also sometimes referred to as Coulomb gluons. These are the gluons that are they are not collinear to the target. They are not collinear to the projectile. They're sort of soft all the way around. They only carry a transverse kick. They do not disturb at all the large plus and the large minus that are punching straight through each other at the speed light. So that's the kinematics of high energy scattering. Any other questions so far?
Matt,
Yes, please.
to ask, like, it's a bit earlier on when you drew the cut diagram.
I'm sorry, I'm having a hard time hearing. Can you speak up, please?
I think it's earlier on when you drew the cut diagram, when you were, working out, M and M conjugate. In the second half of that, sort of diagram, the time reverse part, like,
yes,
which way do the arrows run? What does that matter?
Ah, okay, yes. It's sort of just a convention, but to explain what I was doing there, I should really think of this as, on the left side of the cut, I have the scattering amplitude, where time goes this way. On the right-hand side, I could draw it, or I should draw it as exactly the same thing. Time still going this way, but complex conjugated. The complex conjugate of the right-hand side reverses the order of the spinor traces, like we saw. If I had U bar 1 gamma U1 prime, and I conjugate it, I basically flip the direction of the trace. U bar 1 prime gamma U1. So the effect of complex conjugation on the right-hand side is basically to reverse the diagram. So now I get this thing where it effectively is flowing backwards after having performed the complex conjugation. So that's how you can think about what it means. As far as how to draw it, it's really convenient to draw it like this. As if it's one single diagram that goes from t equals minus infinity through t equals plus infinity and back again to t equals minus infinity all at once. You can think of this as being like the optical theorem. You want to calculate the amplitude squared, which is the imaginary part of the forward scattering amplitude. This cut represents taking the imaginary part. And this is a well-defined overall amplitude that actually does go from minus infinity back to minus infinity all the way through plus infinity. This is also related to this Schwinger-Keldysh formalism where you describe simultaneously the propagation in the amplitude and the complex. So I think you can The reason the arrows are drawn this way is it already performs the reversals. So now I'm going backwards from final state to initial state. And the nice thing about it is that it correctly describes in the Feynman rules the overall answer. So that when I got P1 prime, P1, gamma mu, gamma nu, I could have just looked at this diagram and read off the answer without thinking about it. That's a single trace that I compute using the Feynman rules like always. It's going to give me trace of P1 prime slash gamma mu, P1 slash that wraps all the way around gamma nu. And that is the correct answer. That is exactly what I get if I take this numerator times the conjugate of that numerator and then sum. So I think that's the reason for drawing it this way, that it correctly describes the Feynman rules at the level of a forward amplitude from initial state back to the initial state. Does that help?
Oh, okay, thank you.
Okay, great, no problem. Okay. So I hate to tell you, that was the warm-up calculation. The real thing, the real main point is the next to leading order calculation, where now we want to include not just quark-quark scattering, but quark-quark plus one gluon. So now the challenge is to go to NLO, next to leading order. The process that I have in mind is now quark-quark goes to quark-quark plus glue. This is now inelastic scattering, in which a new particle is created in the final state. I should be clear what I mean. This is NLO if I'm talking about an inclusive cross-section. So this would be NLO contribution to say quark-quark goes to anything, where at lowest order, the final state contains quark-quark, and at next to leading order, the final state can contain quark-quark glue. Of course, if I ask for the exclusive process that must produce the final state, this isn't next to leading order anything, it's the leading contribution to that. But if I'm talking about an inclusive cross-section, then the answer we just calculated a second ago, elastic quark-quark scattering, contributes along with the inelastic NLO process. So that's what I have in mind. Again, we want to calculate this in Reggie kinematics. So I can think of this as being a modification of my previous diagram, the T-channel diagram. P1, P2, P1 prime, P2 prime, where now I'm going to add in an extra gluon radiation, one gluon Bremsstrahlung vortex. And there are many ways that I can do that. I could have final state radiation off of P1 prime, or I could have final state radiation off of P2 prime. I could also have initial state radiation off of P1, or initial state radiation off of P2. Also, because now QCD is a non-abelian gauge theory, I have another fifth unique possibility, which is that I can have Bremsstrahlung directly from the T-channel gluon being exchanged. So there are actually 5 diagrams corresponding to 5 possible emitters. And in principle, we have to sum them all. I am not going to have time to do all of these calculations on the board. I'm going to do a couple of them in great detail. I will argue a couple of more of them as symmetry transformations from the ones that we got, and then I will just state the answer for the last one. So the ones that I'm going to focus on primarily are what I call in the notes diagram A and diagram B. This is the final state and initial state radiation cases A and B. So this is my final state interaction. This is my, let's say, final state radiation. And this is my initial state radiation diagram. The ones where the radiation comes off the lower leg, I can just get by symmetry from these ones. The triple gluon vertex one is a nice calculation. It's just a little bit time consuming to get all the algebra right. So that's the one that I will just state. So I'm still interested in Reggie kinematics. I want S going to infinity. I want Mandelstam T constant so that I still have that P1 minus 2 plus, where the minus and the plus momentum mostly flow straight through. But now if I have an extra particle in the final state, I have to be more careful with the kinematics. If this is a gluon with momentum k mu, I have to specify what kind of momentum k mu I'm producing. And for this, I'm going to work in a particular region where the gluon is soft compared to both the large P plus of the target and the large P minus of the projectile. So I want to choose to look at particle production in the region where K minus, the gluon minus momentum, is very, very small compared to the big minus momentum in the problem, P1 minus. But it's still large compared to the smallest minus momentum in the problem. That would be the minus momentum of P2, the thing that's going mostly along the plus direction. Much, much greater than P2 minus, and P2 minus is of order some transverse momentum scale, the mass, some other transverse momentum recoil divided by P2 plus. So in terms of my power counting, whenever I see K minus, I'm going to assume that K minus is really small compared to the big minus momentum here. But the K minus that's coming out here is large compared to the absolutely negligible minus momentum that lives down here in this part. In the same way, I want my K plus to be much smaller than the big plus momentum, P2 plus, but not so small that it starts to compete with the on-shell plus momentum of P1. So this needs to be much larger than P1 plus, which is some transverse momentum scale over P1 minus, which is large. So this is the range that I'm going to choose to focus on for the particle production. This region has a particular name that is of high experimental relevance. This is the mid-rapidity region. So in terms of the rapidity, y equals 1/2 log k plus over k minus in this case. This means that I'm looking at particle production near y equals 0. Let's say the absolute value of my rapidity is much, much less than the total rapidity interval of the collision. What does that mean? If I have my light front plus direction, my light front minus direction, rapidity is the ratio of plus over minus in logarithmic units. So y equals 0 means that you had something that came out exactly rest along the beam line. It's not going forward in PZ, not going backward in PZ. It may be moving transverse, but it came out exactly perpendicular to the beam plane. Because of the logarithmic spacing, the rapidity goes to plus infinity when you get to the forward light cone. It goes to minus infinity when you get to the light cone minus direction. And in between, you have these slices of constant hyperbolic angle. 1, 2, 3, 4, up to infinity, and so on. So what we're talking about here is gluon production in the region at mid-rapidity, where I'm not close to the fragmentation region of P2. I'm not close to the fragmentation region of P1. I'm sitting nicely in the middle. In terms of an experimental setup, that means that I'm looking primarily at particle production in the barrel. So that if I have an interaction point here, mid-rapidity is all the particles that are coming out not super forward along the beam pipe, not super backward, right there along the detector where you have perfect full azimuthal coverage. So this is a very experimentally relevant regime. It's also the regime that is very sensitive to this small x dynamics, both in projectiles. Okay. I'm not sure how far we're going to get through the calculation before we run out of time today, but I'll push as far as we can so that we can end on a good note tomorrow. Okay. So again, I need to specify the kinematics. If I draw that diagram A just for concreteness, I have P1 coming in, P2 coming in, Let's call the exchange momentum here Q, like I probably should have done the first time. Then this is P2 plus Q, and this is P1 minus Q. If I call the gluon, which is coming out, momentum K, then the remaining quark, which is coming out, is P1 minus K minus Q. All right, I want to set up my kinematics. Again, I have my initial state freely chosen by my frame. So I'm going to pick P1 to have nothing along plus, big momentum along minus, and nothing in the perp direction. P2 I pick to be mostly along plus, nothing along minus, nothing along perp. My K mu is the final observed gluon. It has some momentum K plus. It's on shell so that its minus component is K perp squared over 2K plus. And it has some transverse momentum K perp. The only other momentum that I need to figure out is Q. Q has some transverse momentum Q perp. But like I sketched a second ago, I can figure out something about Q plus and Q minus from the on-shell conditions of the other particles. My large plus momentum is down here in terms of P2. So I can use that to solve for Q minus. Q minus is P2 plus Q's minus component. Take away P2's minus component. P2's minus component is exactly 0. P2 plus Q's minus component is Q perp squared over 2 P2 plus Q plus. And as we'll show in a moment, P2 plus is much larger than Q plus, so I throw that away. And this is Q perp squared over 2 P2 plus. This is again the same region as what we had before, where my Q minus is much, much less than P1 minus. So I found the minus component. That is Q perp squared over 2 P2 plus. I can similarly find the plus component. So Q plus I have to get from the upper part of the diagram. Q sits here in terms of P minus K minus Q. So if I subtract P minus K minus Q plus component, and I cancel it out against P1's plus component and K's plus component, then I'm going to get back Q plus. P1's plus component is exactly 0. K plus is one of the variables that I want to keep as free and express my answer in terms of. This one is on shell. Its plus momentum is K plus Q perp squared over 2 P1 minus K minus Q minus. We just showed that Q minus is tiny, so I can ignore it. K minus is tiny by assumption because I'm looking at particle production at mid rapidity. So this second term is minus K plus Q perp squared over 2 P1 minus. And as we just said, my K plus is supposed to be small, but it's not so small as 1 over P minus. So in the region that I'm looking at, this term is negligible compared to this one. And I get Q plus is approximately equal to negative K plus. Okay, so I've specified my kinematics, all of the 3 variables, P1, P2, K, and Q. Now let's start to compute the elements that will be necessary for my diagrams. Both of the diagrams are going to have numerator algebra in terms of U's and U bars and color factors. That I have to deal with individually. But both of the diagrams have the same Q propagator. So all diagrams will have 1 over Q squared, where Q squared is 2Q plus Q minus minus Q perp squared. My Q plus is negative K plus. My Q minus is Q perp squared over, 2P2 plus minus Q perp squared. So 2's cancel, K plus over P2 plus Q perp squared minus Q perp squared. The first term is much smaller than the second because the first term is proportional to the small K plus divided by P2. So I can ignore the first term and I just get the virtuality Q squared is approximately negative Q perp squared. That's that Glauber gluon that we just said a moment ago. That's basically unmodified from the leading order diagram. The other thing that I need to calculate in terms of virtualities is the intermediate state propagator. That one is different from diagram to diagram. So for diagram A, which was this final state radiation case, I need to calculate P1 minus Q squared. P1 minus Q squared is 2, P1 plus minus Q plus, P1 minus Q minus Q per squared is the transverse momentum component. And now I fill in my kinematics. P1 minus is large in comparison to P1 minus. Q1 minus is negligible. On the other side, P1 minus is 0, so I only have negative Q. So I get negative 2 Q plus P1 minus Q per squared, and my Q plus is just negative K plus. So this is positive 2 K plus P1 minus Q per squared. P1 minus is huge. K plus is small, but it's not so small that it gets rid of that P1 minus. So compared to the first term, the second term is negligible in this mid-rapidity kinematics that I'm working in. So this intermediate state virtuality I get is approximately 2K plus P1 minus. When I do the other diagram, I'm going to have a slightly different intermediate state propagator. For the initial state radiation diagram B, I have P1, P2, K, P2 plus Q. This is Q. This is P1 minus K, and this is P1 minus K minus Q. So whereas before my propagator was P1 minus Q squared, for the initial state radiation diagram, it's going to be P1 minus K squared. And I work this out in the same way. 2 P1 plus minus K plus, P1 minus K minus K per squared. Again, P1 minus is huge. In comparison, K minus is negligible. P1 plus is 0. So I get negative 2 K plus P1 minus K per squared. And again, that P1 minus is the largest momentum in the problem. That K per squared can't compete with it. So I get negative 2 K plus P1 minus. Let me pause here for a second before I go on, because the critical difference has just appeared between the initial state and the final state diagrams. What turns out, as we'll see momentarily, is that kinematically, the two amplitudes are identical. A and B are equal to each other with exactly the same dependence on all the momentum variables, except for a minus sign. That minus sign is this minus sign. This one is negative, this one is positive. It comes completely from the fact that this intermediate state, when I had final state radiation, this P1 minus Q is time-like. When I square it, I get something positive. This one, however, the propagator for the initial state radiation is space-like. When I square it, I get something negative. And that's why, in a moment, when I add these two diagrams together, they are desperate to cancel each other. In QED, that's exactly what happens. They cancel each other and you get 0. In QCD, it's much more interesting. Okay, so we've got all of the ingredients. Now let's just put together the amplitudes and combine them. Easier said than done. Let's start with that diagram A. So my amplitude for diagram A, if I do the same thing as before, I start with this final state quark and work backwards. I have a spinner. Let me call this P1 prime for abbreviation. Call that P2 prime for the same reason. So up here I have U bar of particle 1 prime. I have this emission vertex, which is IG TA gamma mu. I have this propagator, which is I P1 minus Q slash over P1 minus Q squared. I have another vertex, which is IGTB gamma nu. And then I have my initial spinner U1. That takes care of the numerator algebra for the upper line. For the lower line, I have U bar of particle 2 prime. I have the matching vertex here. So let's see, I picked color A for the gluon here. B is the color on this gluon being exchanged. I picked mu for this vertex and nu for this one. So down here, I get IGTB gamma upper nu, U of particle 2. And then I have the gluon propagator, which is minus I've already used the G nu nu prime divided by Q squared. And the last thing that I have is the on-shell polarization vector for the produced gluon. That is epsilon K, if I pick a particular polarization state lambda, it's epsilon K lambda with index mu, and since I'm producing it, it's okay. So if I clean up the structure and write it in a compact form, what I get is I G cubed over Q perp squared 2K plus P1 minus TA TB I prime I TB J prime J times the spinner product U bar 1 prime epsilon lambda slash star up times P1 slash minus Q slash gamma nu U1 times U bar 2 prime gamma nu U2. Okay. So we've constructed the amplitude. This is the 1 over Q squared from the Glauber-Gluon exchange. This is the virtuality of the intermediate state, the P1 minus Q squared that was here. The numerator algebra here on the right starts with the U bar, and then I have vertex P slash vertex U. That's this product of 5. And then I've got the simple product of 3 from the lower line like before. So clearly I should not try to solve this problem the same way we solved the last one. The last one, we took the full amplitude with all of its structure, we added all the diagrams, we squared it, and only after the fact did we take the Eikenal limit, the high energy Reggie kinematics. If I try to do that here or at higher order diagrams, it's going to get terribly messy. It's going to be very hard to propagate that forward. So instead, it's very preferable to, if I can, use the Eikenal approximation here at the amplitude level to simplify it before I combine things. So let us so-called Eikenalize the amplitude. So I'm going to try and use the intuition that we just built off of the quark-quark scattering case to identify the leading high energy pieces of this expression. So first things first, I'm going to start with this simple spinner product on the lower end. This is exactly what we had before. And the kinematics of this process is that I had a large plus momentum that basically goes straight through. My P2 mu basically had P2 plus and nothing. And my P2 prime mu still basically has the same P2 plus, not much minus, and I guess it has some transverse momentum, but who cares compared to P2 plus. So the first argument that I'm going to make is that even though P2 prime is a little bit different than P2. To a great approximation, this thing is basically U bar where the momentum is P2 plus, just that plus component. Gamma nu U2 of just P plus. So if I ignore all of the other momentum components that are much, much smaller than that dominant P plus momentum, then this is a matrix element of the same momentum. And that's really nice because I can evaluate that using the Gordon identity. I get a factor 2 P2 plus, but only if nu is equal to plus. So I could write it as, let's say, delta nu plus. This thing also comes, by the way, with the Kronecker delta of spins, S2, S2 prime. This is sometimes referred to as the eigenal vertex. This is what happens if I have a particle whose only momentum is the light-like momentum. I get the factor of the large momentum that comes out. I get something which is insensitive to spin, and I pick out just the vector component in the direction of that momentum. So I can use the fact that basically this element only has a large P2 plus in it to simplify it and write that whole thing as 2 P2 plus delta nu plus, and then I'm not going to worry about writing the spin part explicitly. So that simplified the lower part of the diagram, this piece, using the information we learned previously. Now, once I specify nu, I learn nu equals plus. That has other implications for the upper part of the diagram. So if I take that delta nu plus, I can use that here for the other gamma. So after I sum over nu, I get gamma upper plus here at the end. So then after that, the other numerator factor that I'm left with is U bar 1 prime epsilon slash lambda star P1 minus Q slash, and then I have, oh, sorry, this was gamma lower plus, lower nu here. So I put nu equals plus, this is gamma lower plus. Gamma lower plus is the same thing as gamma upper minus. So that is gamma minus U1. Okay, so now I want to simplify this numerator factor, and my hint is the fact that I have the same large P1 here in the middle of it. The largest momentum here in this intermediate state propagator is P1 minus, and if that's a slash, it has to go along with gamma plus. So if I just pick out the dominant momentum component of that intermediate state, then this should be approximately equal to P1 minus times U bar 1 prime epsilon lambda slash star gamma plus gamma minus U1. Now I can further simplify that expression because I know the Dirac equation. So in particular, I know P1 slash times U1 is equal to 0 in the massless limit. And this argument tells me that this is P1 minus gamma plus U1 is equal to 0. So gamma plus times U1 is equal to 0. So that means my gamma plus is sitting here. If I commute the gamma plus over, I'm going to get 0 as soon as gamma plus sits next to U1. So without loss of generality, I can replace these things by the anti-commutator because the term that I'm adding is 0. And if I make this the anti-commutator of these two gamma matrices is a factor. So we're continuing to simplify the numerator structure as we go. That big long trace of, product of 5 has simplified to U bar 1 prime epsilon lambda slash star. I get a factor of 2 E1 minus And then I go straight to U1 here. Now I've boiled this numerator factor down to the same kind of U bar gamma U structure that we had in the lower part of the diagram. By the same logic, this is overwhelmingly dominated by E1 minus. So by the Gordon identity, this one should give me 2 E1 minus epsilon star. Yes. So that 2p1 minus multiplies the epsilon star that goes along with it. And with that, we've completely evaluated the numerator algebra directly at the amplitude level, which is pretty awesome. When I put it all together, I get amplitude for diagram A is IG cubed 2s over q perp squared, epsilon lambda star plus component over k plus, and then I have the color algebra TA, TB, I prime I, TB, J prime J. And then if I want to, I can write the spin Kronecker deltas explicitly, delta S1, S1 prime, delta S2, S2. Okay. So this was the result of our calculation for diagram A. You can almost immediately guess what the answer is going to be for diagram B. So diagram B, we said, is going to differ by a minus sign because of the change of that intermediate state. The other change is that the color factor, the color matrices come in the other order. So for diagram B, I get minus I g cubed 2s over q perp squared epsilon lambda star plus component over k plus. Now I have TB TA, I prime I, TB, J prime J. And again, the Kronecker delta spins if you wish. Okay. So finally, we've arrived at the point. This is the sum of the final state radiation diagram A plus the initial state radiation diagram B. As advertised, the high energy kinematics in Reggie kinematics, as S goes to infinity, the kinematics of these processes are exactly the same. I have a large minus momentum that goes straight through. I have a large plus momentum that goes straight through. And I bleed off a very tiny amount of plus and minus momentum to be able to create a gluon in between. So none of that really changes very much when I go from final state radiation to initial state radiation. The only thing that changes is the relative flow of those plus and minus momentum. So if minus is going straight through here, maybe let me draw it a little bit differently. Say I have 100, or let's say a fraction 1 of my minus momentum to begin with. And my gluon at the end carries out a fraction x of it. So that 1 minus x is the amount of momentum that remains, and there was basically zero minus momentum that got exchanged here. So in this case, the minus momentum is flowing like this. It goes forward along the top and it branches, a collinear branching. Plus momentum flows just down along the bottom. And in order to put this gluon on shell, I take a tiny amount of plus momentum and send it up, just enough to make this gluon on shell. The point is the relative flow of momentum on this propagator. In that intermediate line here, I have minus momentum going forward, and I have light cone plus momentum also going forward. So when I get that 2 E1 minus Q plus or K plus, I get something positive. Because here the plus and minus momentum are flowing together in the same direction. That's the difference in this diagram. In order to send a little bit of plus momentum to the gluon, I have to send it up and then backwards. So the plus momentum is flowing to the left, but the minus momentum is flowing to the right. That misalignment of plus and minus is what makes that propagator negative. And that's what leads to the sign difference. So this substantiates what I was saying yesterday. If I take these two amplitudes, A and B, if I for a second turn off QCD, if I go back to electrodynamics, and this is a photon instead of a gluon, not much changes. The kinematics doesn't change. My color factors go away. These are just one, but everything else is basically the same. So if I was doing electrodynamics, I would have negative number plus same positive number equals 0. And that tells you that the amplitude to radiate a photon in high energy Eichenal scattering of electrons is 0. You don't radiate power of photons because the electrons did not accelerate. If kinematics is the only thing you have. But this is the game changer. Because I have color matrices that appear, and because my initial and final state diagrams have those color interactions in a different order, the sheer fact that this is a non-abelian theory means that when I add those two diagrams together, I am A plus I am B, I do not get 0 in a non-abelian theory. Instead, I get TA TB minus TB TA, which is a commutator of TA TB, which gives me the structure constants IFABC times TC. So the point is, for QCD, when I add diagrams A plus B, I do not get 0. But in QED, I do. So it is a unique feature of the non-abelian structure of QCD that causes this result to be non-zero and interesting. So I think maybe a good place to stop that is to summarize the result of the amplitude calculation. When I add those two things together, A plus B, I get minus G cubed FABC TC TB 2S over Q perp squared epsilon lambda star plus over K plus Kronecker delta of spins. This form with the FABC is exactly the same form as the non-abelian diagram where the gluon is emitted from the triple gluon vertex. That diagram, I don't think I wrote separately, but that vertex you recall from the Feynman rules has that FABC in it. So it is not an accident that by adding up the commutators here, I get something that has an FABC, which is exactly of the right form to add to that diagram E, and get a final answer that contains the FABC. After the full laborious calculation, the final answer for the total scattering amplitude is minus G cubed FABC TC I prime I TB J prime J 4S over Q perp squared epsilon lambda star mu times the product K perp mu over K perp squared minus K plus Q perp mu over K plus Q perp squared. This answer is the result of adding up all 5 of those diagrams. So final state radiation off particle 1, initial state radiation off particle 1, final state radiation off particle 2, initial state radiation off particle 2, plus the non-abelian gluon radiation. All of those diagrams together give you a full gauge invariant set that is the same answer in every gauge. And so this amplitude is the full gauge invariant thing. We calculated it in covariant gauge. You can get the answer many different ways, and there's advantages and disadvantages to all of them. I said that this thing combines into a form proportional to FABC. It looks as if I took all of these other diagrams and turned them into this diagram by adding them all up. You can compactly write the entire thing as an effective 3-gluon vertex. So my sum of all diagrams can be written in the form that looks like that 3-gluon vertex, but with a special Feynman rule that describes that final answer. This is referred to sometimes as the Lipatov vertex. And that's the general answer for summing all of the different processes that can lead to gluon rupture. The final punchline that I'll stop on here is that if I take this amplitude and I square it, I get the cross-section as before. The cross-section is now differential in both the Q perp of the elastic scattering, as well as the variables K perp and Y of the gluon radiation. This answer is 2 alpha S cubed CF over pi squared 1 over Q perp squared, K perp squared, K plus Q perp squared. So that's the final answer. The most important feature of this cross-section is maybe not the obvious one. Some of the features here are model dependent. This was a specific calculation for scattering of one quark off of another quark. The details like the exact transverse momentum dependence that comes in down here, that knows about the fact that I had a single quark here, a single quark there. It would change if it was a meson or a baryon or something else. But the thing that's really, really robust about this is the energy dependence, the square root S dependence. And the fact that this cross-section is a constant with rapidity y. That part is completely generic. So the fact that I have a cross-section d sigma dy equals constant, that is what's going to lead to the game-changing resummation. As we'll show next time, if I integrate over that rapidity window, I get a large log of 1 over x, a large log of the center of mass energy. That is the origin of the competition between the small coupling and the large phase space for gluon radiation. Resumming those logs means resumming soft gluon emission one after another. So that process of collecting and resumming these small x gluon Bremsstrahlung logs is what's going to lead us to BFKL evolution, BK evolution, and gluon saturation. So it is my intention next time to show you as much of that story as possible, at least constructing BFKL, trying to construct BK and understand the nature of its solutions and properties. Okay, I ran a little bit long this morning, so thank you for your patience. I'm happy to answer any questions if there's time.
Are there questions? Motibi, go ahead.
Hi, man. So I wanted to ask, I think you mentioned it earlier in the lecture or something, but I didn't quite get it off, like how you can sort of kind of get a feel of like what S dependence your amplitudes are supposed to have in these things in terms of like.
Yeah, no, I didn't derive that for you at all. I could send you a reference. I don't really know what to say about it off the top of my head. There's a general theorem where you can write down the energy dependence of your cross-section, say the sigma dt for this 2-to-2 scattering, as a function of the spin j of the particle that's exchanged. I believe, if I have it right, that it goes like s to the power, what is it? J minus 1, right? It needs to be s equals s to the 0 if j equals 1. There must be j minus 1 over 2. No, I think it's j minus 1. I have to look up the exact expression. It's in Yuri's textbook. I could go grab it for you in a few minutes. But there's a general theorem. I don't know how to derive it. I can just state the answer that as a function of the spin of whatever T-channel particle is being exchanged, you can calculate the energy dependence. I don't think it's anything magic. I think it's just a matter of that, the counting of the large P minus and the large P plus with the structure of the vertex. So probably if you just sit down and calculate an example, then the point is that you see if you have a vector, you get something which goes like s to the 0, something which is constant. if you have a spinner, you get something that goes like S to the -1. So I don't know, it must be 1 minus J like that. No, J minus 1.
Oh.
I'm writing this thing wrong. This is the correct answer here.
Yeah.
But there's a general statement that you can make for arbitrary spin of the exchange particle. You can quickly check it yourself for a couple of simple examples. This is sort of the punchline that the vector is special, that it's unsuppressed. Anything else you try to exchange is highly suppressed at high energies. So it never makes sense to talk about multiple exchange of quarks, multiple scattering by T-channel quark exchange, because every time you have another one, you lose another power of the energy. The only thing that it ever really makes sense to resum is the vector exchange.
Except if you exchange a graviton. If you exchange a graviton, it'll blow up.
Yes. I wasn't going to let that particular cat out of the bag, but yes, this implies things. If you exchange something which has higher powers of the spin, so then you would get something which grows like a power of the energy. That's very bad as far as things like unitarity are concerned. But we have bigger problems with discovering quantum gravity than that.
And so is this fact approximation dependent? So is it in the iconal, like, or is it just?
So I would say it is subject to iconal kinematics. It is not the iconal approximation. Iconal approximation specifically means I'm writing my expansion of my, I don't know, my scattering amplitude as a function of T over S, where T over S is much, much less than 1. So the iconal expansion means I keep T over S to the power 0, the unsuppressed piece. That's the iconal piece. The first correction to this is T over S to the first power. That's the first sub-iconal correction. And there's a whole series of corrections on top of that. So this, like, power counting is based on the idea that S is going to infinity and very large, but it is not limited to the iconal term. This includes terms that goes beyond the iconal approximation. But it's part of the logic that helps you pick out what is the dominant iconal term.
For example, one could say that the iconal approximation is exact in the iconal limit.
Yes. Right. So the iconal kinematics means that I'm talking about. So maybe a better way to say it is that iconal kinematics means S over T is much greater than 1. The iconal limit means S over T is infinity. So I can do a systematic expansion in a large number or a small number, or I can take it all the way to infinity. This is the iconal approximation. This one I would say iconal power counting, or I've been calling it Reggie kinematics. Does that answer the question?
Yes, thank you.
Great.
All right, guys. Thanks, Matt.
No problem. Thank you very much.
As an exercise problem at some point to calculate